In keeping with very typical event schemas, every row in a Druid table data source contains a timestamp and then a set of dimensions, those attributes and measures that record and describe what happened. But how many of these tables do you need? What should you think about? Control over what is being ingested and when is controlled at the table level, as is affinity of the ingestion tasks to the hardware resources. So consider how you're going to manage the ingestion work and to scale it up and down. The segments for each table, the actual data that is pre-fetched for querying, are stored next to one another in deep storage. Now, this might help you if you have a reason to measure or manage storage usage for particular business units or particular use cases, or perhaps to apply logical separation at the storage level for security reasons. The schema for each table stored inside each segment, its definition, comes from how you set up your ingestion. It's also where you might have used a group by or classic rollup to summarize your incoming data. What schema and granularity will you have on each table? And what are your control processes going to be like around the ingestion definitions? This is often a very important design consideration for Druid adoptees, where you need to strike a balance per table between flexibility and performance. Maybe you need several tables from the same source data, each with different schemas and levels of granularity. Your ingestion definition also controls the filters and expressions on the source data. For performance, you might have a table that is effectively a view of the source data, which only contains, say, error details. Your ingestion also defines the partitioning scheme. With multiple tables, you can use different time partitioning and dimension clustering for different query patterns. Druid ingestion also allows for using an existing table as your source, what's known as reindexing. You might create a downstream table on a schedule that has a new schema or level of summarization or transformations or filtering, or of logical separation. Or you might overwrite what's already in there. Auto-compaction applies good layout to stream sources automatically. Especially if you're doing streaming, note that your configuration for automatic compaction is also set per table. Each table also has its own retention rules. From the same source data, you might have one table with one schema that holds 7 days worth of data, and another table with a different schema and a different level of granularity that might hold 28 days worth of data. The retention rules are also where you set what data goes where when the data is prefetched to the query processes. That affects the replication factor, which is about resilience, and it's also about the opportunity for the parallelization of queries. And while the default in Druid is to put everything on all machines, using tiering lets you split up workloads to different groups of processes. You might use this to push queries on older time periods to a set of cheaper machines with more disk and maybe fewer CPUs and less memory. While you may now have lots of ideas about how you could use your source data to create tables, avoid creating hundreds of them in a single cluster without carefully considering the impact on the core processes of Druid, particularly the coordinator as it handles retention and data distribution, and the overlord as it manages your ingestion, your reindexing, your compaction, and data deletion. Take a look at the docs pages on the topics that I've talked about here today, and go and try out some of the notebook tutorials around ingestion and schema design. And on the union all operator, which is quite often used to bring multiple tables together at query time.